Hi. In this video, we will be talking about homogeneous equations. As you remember in the last video, actually we studied these definitions. This is how we define homogeneous differential equation, and it is homogeneous linear equation at the same time, because in the equation we do not have the product of y or y prime, or we do not have y squared, anything. Anyway, when we say homogeneous equation, this expression, a term which is not multiplied by y or the derivative of y of any order, actually that is, let's say the g of x is equal to 0 here. So we call this homogeneous equation. If it is not equal to 0, on the right hand side we have a function of x here, and that's called non-homogeneous. Throughout this video, I will be mentioning these two equations, equation 6 and equation 7, that is homogeneous, and this one is non-homogeneous. So you should keep them in mind. Differential operator. In calculus, differentiation is often denoted by the capital letter D. That is dy dx equals dy. See here why we are introducing this. As we go further, you will see that every time writing this expression may not be convenient. Okay, it's a kind of compact notation. Okay, and also when it is this, it's really easy to, how to say, transform differential equation into the auxiliary equation. So anyway, here our notation is dy dx. We are denoting with dy. That means that here, what does this d differential operator here? It is actually d dx, right? So the symbol d is called differential operator because it transforms a differential function into another function, right? You're differentiating, for example, if you differentiate x squared, its derivative is 2x, right? Or if you differentiate sine of x, its derivative is cosine of x. That's why it's performing some kind of transformation. That's why it's called differential operator. So in general, we define an nth order differential operator or polynomial operator to be that L equals a sub n of x, d to the power n, and blah, 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 blah. Okay. So if the order is 2, for example, let's say if you're given y double prime plus 3y prime is equal to x. Okay. And another way, how can I write this equation? Either I can write in this way, right? D squared y over dx squared plus 3 dy over dx is equal to x. And how about using this differential operator? You will see that when we use this differential operator, it was quite simple. And actually, it really, how to say, makes the solving procedure, the solution procedure quite faster when we are dealing with differential equations. Here I can write this in this form, this d double prime, that is d squared y plus 3 times, what is y prime? It is dy is equal to x, right? As see here now, y is a common factor. Simple, I can just write it as d squared plus 3d times y is equal to x. Actually, this equation, or this equation, all they describe the same thing. And here, differential operator L possesses a linearity property. That is, L operating on a linear combination of two differential functions is the same as the linear combination of L operating on the individual functions, right? So in symbols, this differential operator on alpha times F plus beta times G produce the same result as alpha times L, this operator on F plus beta times L on G, where this alpha and beta are constants. So because of this line, we say that the nth order differential operator L is a linear operator. And also actually, as you see, it's very similar what we have learned in linear algebra, right? Linear transformation. It has two properties. In general, those two properties in general form is described by this equation. some examples used for related to differential operator about how we use the differential operator. Any linear differential equation can be expressed in terms of the D notation. For example, y double prime plus y prime plus 6y equals 5x minus 3, right? So this y double prime, it can be replaced with d squared y, right? This differential operator, but the order is true here. That means that we are differentiating y twice. And here we are differentiating y one time. And it is no derivative here. On the right-hand side, we have 5x minus 3. As you see here, this y is a common factor. And take this out, we will have this equation. D squared plus 5d plus 6 times y is equal to 5x minus 3. Okay. So using 8, we can write the linear nth order differential equation 6 and 7 that we have mentioned a few minutes earlier, compact as L of y is equal to 0 and L of y is equal to g of x. That is our homogeneous differential equation, right? This one is non-homogeneous linear differential equation. And you remember this L. What is it? It's just differential operator of nth order. So superposition principle, homogeneous equations, we have already studied in the previous class. I'm going to skip this. We will continue with linear dependence and linear independence. These two concepts are very basic to the study of linear differential equations. And also, you studied a similar concept in linear algebra. But in linear algebra, linear dependence and linear independence of a set of vectors. But here, we are going to define this linear dependence and independence concepts for functions here. Since actually we're talking about functions in differential equations. A set of functions, this f1, f2, and fm. Assume that we are given a bunch of functions, is said to be linearly dependent on an interval I if there exists constants C1, C2, and C sub n, not all zero. Not all zero means at least one of them is not equal to 0. Okay, such that linear combinations of these functions is equal to 0. So if you can find such a set of these numbers, constants, C1, C2, C sub n, at least one of them is not equal to 0, because if all of them are equal to 0, it's always equal to 0, right? So is it possible to find one set of these constants, C1, C2, C sub n, at least one of them is not equal to 0? When you just multiply the first function by C1, the second function by C2, and the last function Cfn by Cm, and their linear combination produces 0. That is identically equal to 0. Is it possible? If it is possible, we say that these functions, this f1, f2, and f sub n, they are called linearly dependent. Okay. For every x in the interval, if the set of functions is not linearly dependent on the interval, it is said to be linearly independent. Okay. Just one example. For example, let's say we are given these functions. F of 1 is equal to 1, for example. F of 2 of x is equal to x. F of 3 of x is equal to, let's say, x squared. Okay. Are these functions linearly dependent or independent? Can you just find three constants where C1 times 1 plus C2 times x plus C3 times x squared is equal to 0. Is it possible to find these constants? Actually, it is never possible, right? It's never possible. You cannot find where all, not at least one of them is not equal to 0. That's always equal to 0. If you just take what is our interval here on the number line, because they are defined everywhere on the real number line. Okay. Right. So actually for this expression to be equal to 0, the C1 and C2 and C3, it must be equal to 0. That's the only solution of this equation. All right. We do not have any other sets. At least either C1 or C2 or C3 is not equal to 0. At least one of them is not equal to 0. And its linear combination is equal to 0. All right. But if we just pick something like, for example, let's say if I just add one more function here, let's say it is 2x plus 3x squared. Now if you consider f1, f2, f3, f4, are they linearly independent or dependent? Okay, and you will see that linear dependent means when we talk about a bunch of functions, if they are linearly dependent, it is possible that at least one function can be expressed as a linear combination of the remaining functions. Okay, but as you see here, this function is just simply a linear combination of what is it, f2 and f3, right? If I just multiply this f2 by 2 and multiply f3 by 3, so it's just equal to 2 times f sub 2 plus 3 times f sub 3, right? So actually this means that if I just add this function now, this set becomes linearly dependent, all right? And if I just remove this, these functions, it is linearly independent. Why? Because I can find, if I just write here, the C1 times F1 plus C2 times F2 plus C3 times F3 plus C4 times F4. Can I find four constants C1, C2, C3, C4? At least one of them is not equal to 0, where this thing produces 0. Is it possible? It is possible, right? Because here, as I say, this F4 is just a linear combination of this thing, 2 times F2 and 3 times F3. And instead of F4 and substitute here, and if I just write here this C1, F1 plus C2, F2 plus C3, F3 plus C4. What is F4? F4 is 2 times F2 plus 3 times F3 is equal to 0. Now here we have F2, F2, right? And here we have F3, F3, right? And the coefficients are C, this one coefficient of F2, it is C2 plus 2 times C4, right? And this thing is C3 plus 3 times C4. So that means that if I just choose like this, C1 is equal to 0, right? And C2 plus 2 times C4 is equal to 0. And this thing, C3 plus 3 times C4, 3 times C4 is equal to 0. Because we know that this F1 and F2 and F3, these functions are linearly independent, right? The only way the linear combination is equal to 0, identically equal to 0, is when the coefficients are all equal to 0, because we have no any other possibility here. Now, as you see here, if you just solve this system, actually its solution is not trivial, right? C1 equals 0. From here, C2 equals 2 times. From here, C1 equals 0. C2 is equal to minus 2 times C4. And what is C3? It is minus 3 times C4, right? So how many actually possible combinations we have here? Infinitely many, right? Because this C4 is here independent variable. If C4 equals 1, at the time C2 equals negative 2, C3 equals negative 3, we have one combination. C1 equals 0. For example, one is C1 equals 0, C2 is equal to minus 2, and C3 equals minus 3, and C4 is equal to, what is it? 1. C2 equals 0. Okay, this is one combination. As you see here, at least one of them, actually not one of them, 3 of them is not equal to 0, right? If we just substitute here, C1 equals 0, C2 equals negative 2, C3 equals negative 3, C4 equals 1, that's equal to 0. So that means that this F1, F2, F3, and F4 actually these functions are linearly dependent. See here why at least one of the functions, this C4, for example, I can express this as a linear combination of this 1x and x squared. Example 5, linearly dependent set of functions. Let's consider this example on the interval minus pi over 2 to pi over 2. Cosine squared of x, sine squared of x, secant squared of x, and tangent squared of x. All right. So, are they linearly dependent or independent? So, is it possible that the linear combination, this f1 c2 times f2 plus c3 times f3 plus c4 times f4 is equal to 0? At least, not at least one of C1, C2, C3, C4 not equal to 0. Okay, is it possible? All right, or can you just find four numbers C1, C2, C3, C4, providing that at least one of them should be equal, not equal to 0, so that when I just substitute here, the linear combination of these functions must be identically equal to 0. Okay, I see. Immediately, I think just think of this identity from here. What is cosine squared of x and sine squared of x? How they are related to each other? We know that sine squared of x plus cosine squared of x is equal to 1. And how about this one? We know that 1 plus tangent squared of x is equal to secant squared of x, right? So see here, this thing, right, this f1, that means that here, let me just write here, this f1 plus f2 is equal to 1, right? And from here, what is it? This one is f3, this one is f4. So f3 minus f4 is equal to 1, right? So just considering this, if we substitute there, from here, what is C1? C1 times F1. What is F1? Okay, let me just keep it here. Plus, and the C2 times F2. What is F2? 1 minus F1, right? And the plus C3 times F3. Let me just write here, F3 plus C4 times F4. What is F4? F4 is F3 minus 1. Okay, so that is equal to, from here, right? Here we have C2. Okay, I have C2, right? And here we have F1, C1 plus, here we have C1 minus C2 times F1. Plus, how about here? Here we have negative C4, all right, and F3 is common factor. So here we have C3 plus C4 times F3, and minus C4 is equal to 0. Actually, here this C2 minus C3 is just a single constant, right? If you just evaluate this, when is equal to 0? I mean, is it possible to make this 0? If I just pick all of them as 0, for example, this C2, C4, right? C2 minus C4, just one solution is equal to 0, and C1 minus C2 is equal to 0, and C3 plus C4 is equal to 0. If you solve this, what do you get here? C1 equals C2, right? And C2 equals C4, right? And C4 equals minus C3. That means that if I just pick this one solution, let's say C1 equals 1, C2 will be 1. And C3 will be, and also C4 from here is equal to 1. C4 equals minus C3, that is minus 1. And C4 is equal to 1. And actually, I just show here one combination, right? You see here, at least one of them. Actually here, not one of them, all of them are not equal to 0. So if I just substitute here, 1 times F1 plus 1 times F2 plus negative 1 times F3 plus 1 times F4 and evaluate this, and you'll just end up with 0. Okay, that means that actually these functions are linearly dependent. Okay. If there's only one case that the linear combination is equal to 0, when all of these coefficients, C1, C2, C3, C4 are equal to 0, at that time these functions are called linearly independent. Another example, linearly dependent set of functions. Consider the following functions on the interval from 0 to positive infinity. So square root of x plus 5, square root of x plus 5x, and x minus 1, and x squared, right? So I'm just write them here. Is it possible to find that c1 times square root of x plus 5 plus c2 times square root of x plus 5x plus c3 times x minus 1 plus c4 times x squared is equal to 0. So can I find the c1, c2, c3, c4? At least one of them is not equal to 0. If so, then this set will be linearly dependent. Otherwise, it will be a set of linearly independent functions. Okay, how do we do this? And the rest is just simple algebraic manipulation. First, I need to remove the brackets and write them in a more simpler way. Here we have square root of x. Here I have square root of x. So I can just write it as c1 plus c2 times square root of x, right? And here we have 5c1. Okay, I'll write them here. And how about x? Plus, here I have c2 times 5x. So here we have 5 times c2. We have also x here plus c3 and no more x. So there's x here plus now x squared. I don't have x squared here. We don't have x squared here. So here we have x squared, c4 times x squared, and all the constants right here. What we have here, 5c1, right? And how about here? Nothing. How about here? Minus c3, and is equal to 0. Okay. Actually, it's not equal to 0. We are saying that identically equal to 0. Because for every x, this polynomial or this expression should be equal to 0, right? So here, the square root of x, this x, and x squared, and c1, 5c1 minus c sub 0. On the right-hand side, we have 0. Like 0 times square root of x plus 0 times x plus 0 times x squared. So when is equal to 0? If and only if the c1 plus c2 is equal to 0, 5c2 plus c3 is equal to 0, and here we have c4 is equal to 0, and 5c1 minus c3 is equal to 0. Right? So from here, let me just get one of them. Here c1 equals c2, right? 5c2 plus c3 is equal to 0, and it's 5c1, c3 is equal to 0. And let's say, because I'm just looking at this one possible combination, right? One possible set of these constants. Let's say c1 equals 1. If c1 equals 1 from this equation, c2 equals negative 1. And from this equation, c3 is equal to, c3 equals negative 5 times c2. c2 equals negative 1, so is equal to 5. And what is c4 is equal to 0. So if I substitute here 1, and here we have negative 1, right? And here we have 5, and c4 equals 0. So this thing will be identically equal to 0, right? As see here, we have just found actually a set of 4 constant numbers. At least one of them is not equal to 0, but actually here, 3 of them, right, is not equal to 0. So what does it mean? That means that the given set, this f1, f2, f3, f4, these functions are linearly dependent on the given set. Okay. All right. All right. Solutions of differential equations.